Well, hello there folks, and today we will be looking at the custard cream and whether dunking that really does, as Charlie says, match up to a ginger biscuit. I don't think so. But anyway, today's an exciting day because we're going to be looking at the number E, which you may have heard of, maybe not, I don't know, named after a chap called Euler, but that's spelled E-U-L-E-R, and it's one of the irrational numbers, such as pi or whatever, one of the ones you can't exactly identify. It starts 2.7, goes on and on and on, never repeating, and it's got some great applications for solving some real problems, which tomorrow's lesson will start to have a little look at. For today, it's all very much about pure maths, so have a look at this. In yesterday's lesson, we were looking at, amongst other things, y equals 2 to the power x. Now that is the red line on here. The blue line is what would happen if you differentiated it. So this is the plotted, I think, of the gradient of this, and it's very, very similar, but a little bit below. You do not have to be able to differentiate that as an exact value yet. That comes up in year 2. I don't want you to worry about that, but if you did, that's what you would get, and we do need to know that at the moment. Now moving across here, this is what you get if you did y equals 3 to the power x. The gradient function would give us this line here. Why is it switched colours there? That's very annoying. Actually, y equals 3 to the x. Oh yeah, sorry, the red line is what we're looking at. That is y equals 3 to the x. I know that because when 0 is x, 3 to the power 0, anything would be 1, won't it? So this is actually the blue line is what I get. I got this off an app called Desmos, which is one of Mr. Cooper's favourite websites, and there's a link to this on today's class charts, so have a look at it. You can play around with different values. I'll leave you to work that out, but anyway, here's the gradient function line, the blue line going through there. Now that line, you may have noticed, is now slightly above here instead of being slightly below it, but other than that it looks very, very similar. Now if we move along to this one, this red line here is what we get for y equals 4 to the power x, and the blue line is the differential, the gradient function of y equals 4 to the power x. So it's going further the other way, and if I was to have y equals 1.5 to the power x, that would be coming over here somewhere. So that red line would be, sorry, that red line would be going in comparison to that would be more to the left hand side. So in between 2 and 3, we get to a point where the red line and the blue line match up, and they match up exactly when we get to that special number that I was just talking about, E. So this is the graph of y equals e to the power x, and E equals 2.71828, and so on. You don't need to know exactly what it's equal, but what you do need to know is the ramifications of this, and for that we've got some rules for how to differentiate for e to the power x and things like it. And whilst I eat my biscuit, I'd like you to freeze the next frame when it comes up, and you need to copy down all of it. Right, here's our first examples. In order to do this, we need to use the second part of the things that you copied down, where the 4 would be the k. So maybe have a little go at that, pause the video before you watch me go through it, and see if you can get it anyway. So for the first one, we're going to need to say that y is equal to e to the 4x, so I could have said the function of x. I'll do that on the next one. And then therefore the differential dy over dx will be, we multiply by however many x's we've got, which is 4, and then the power stays exactly the same. That's the beauty of e. It means we don't have to do anything to the power. For part b, let's say this is the function of x this time is equal to e to the minus a half x. Therefore, when we differentiate, that would be multiplied by the k, which is minus a half in this case, e, and then we keep the power exactly the same. One last one to go. C, we've got which way should we go this time? Let's go y. Y equals 3e to the power 2x, and that means when we differentiate that, we'll get multiply by the 2. Well, 3 times 2 is 6, so it'll be 6e to the power 2x, and that's all there is to those. So here's the next example, or 3 examples. So write it down. What we're going to have to do is sketch all of the equations and give the coordinates of any points where they cross the axes. Effectively, that's generally the y-axis, but not always, only then. And state the equations of any asymptote. So pause the video, have a little go, but I would say use your calculators, because that's the way I'm going to show you to do it. And it's also the easiest way to do it. So if you go into your calculator and start off by popping in y equals 2 to the x, just in case you're not sure. Oh, we should I'll delete that actually and show you how to, where e is on the calculator, just in case you haven't found it. So there's e, so we need shift and e, and then it's got power. You can stick whatever you like in there, so 2x goes in there, hit draw, and we can see what we've got there. So we basically know what we need to sketch. In order to make sure we know what that point is, we should know it's 1 from what we've talked about before, but if I hit G solve and y-intercept, it says 0, 1, and that's because anything to the power 0 is 1, of course, and it's never going to quite reach the x-axis, even if it looks like it a little bit there. You can always go in and look closer if you're in doubt. So what that means is we can sketch for A put a 1 in there, and then just need to do something like that. Y equals e to the 2x, and the equation of any asymptote, well, that's going to be the x-axis, isn't it? The equation of the x-axis is the line y equals 0, so asymptote is y equals 0. Okay, and then moving on to y equals 10e to the minus x, just exit that, pop up to there. You don't actually need to delete it, it's quicker, by the way. What are we going for? 10e to the minus x, just to start typing, and it'll disappear because it's all highlighted. 10 shift e to the negative x equals draw, and that gives us something like that. Let's just check on, it's gone higher. I wonder why it's gone higher. Well, let's have a little look at what the value is first of all. So the y-intercept is at exactly 10, and our equation is 10, and that's because e to the power 0 is 1, 10 times 1 is 10, so that's why your y-intercept is 10. So all we need to do there for our little sketch is put a 10 marked up there, and then going all the way down here, and again the asymptote is y equals 0. Now when we said that, that's not really enough, is it? We should also say that that point is 0, 1, and we should say that that point there is 0, 10, because it does ask for the coordinates, and we've only given, strictly speaking, one coordinate there. Right, so that's the first two. Moving along to the third, again, we just hit exit on the calculator, cursor keys to go back up to there, then just start typing 3 plus 4, Shift E, to the power fraction 1 over 2, come out of the fraction and press X to multiply it by that, and then press equals and draw, and ooh, that looks a bit more interesting. Looks like we might have an asymptote a little bit higher. And what would that asymptote be? Well, let's have a little look at what we've got on here. Oh, let's get our, sorry, jumping on, getting overexcited, folks, I'm afraid. Right, so G-solve, y-intercept, there we go, x is 0, y is 7. So why would it have come up with 7? Well, if we start sketching here, we know we've got, we know we're going to have to go through 7, and oh, I haven't drawn this very sensibly, have I? And then we're going, it's doing something like that, isn't it? That's a terrible sketch, but never mind. So we've got the 0.07. It's going through 7 because if all of that, if x is 0, that would be e to the 0 is 1, isn't it? So 4 times 1 is 4, and 4 plus 3 makes 7. And that plus 3 is why it's tailing off so much higher. Our asymptote there is y equals 3, because that 3 that we're adding to it has just moved every value up exactly 3. And that's all we have to do for that. Now I'd like you to have a go at exercise 14b, not every question, but question 1 and 2 certainly, and questions 6, 7 and 8. So if you could have a go at all of those, but before you sign off, I just wanted to show you what you would do for just question 1a, which is just using your calculator to find the value of e to the power x to 5 decimal places if x equals 1. So all you've got to do there is, if we come to menu, go back to 1, and then we are using our, you can see I've done it earlier already, I've showed you how to get to e, haven't I? Shift E to the power 1 and equals, and there we have it. That's all you are doing, and the second one in there, that's there already as well. So that's just getting you used to doing that. So question 1 shouldn't be too onerous. Question 2 will be a similar thing, and then plotting a graph. Then questions, the further later questions start to bring the differentiation exercise into it. Well, I hope you all enjoy that as much as I've enjoyed telling you about it. And see you tomorrow, folks. Goodbye.